Hello, everybody. This is Dr. Richard Smith, and I am here on behalf of the Foundation for the Study of Cycles. And I'm very excited today to have a very special guest, Theodore Modis. And we are here, Theodore is here to talk to us about complexity and entropy and technological change. So I've had a little preview of his work, and it's something that I think that the members of the foundation will find of great interest. And I'm really looking forward to your presentation, Theodore, and to having a chance to ask you some questions as well. So welcome. So can you just begin by giving us a little bit of your own background and interests, and also your interest in cycles, and how cycles factor into your work?
Well, I studied physics from young age. I was passionate about it, and I did research in the Brookhaven National Laboratory, and then that's where I did my thesis, and then later at CERN in Europe. But after many years, I switched to industry and worked for a computer company and Digital Equipment Corporation. You may remember that at some point it was very successful.
Yep.
And then later I ended up on my own because digital was bought by a bigger company, and I didn't want to go sell computers or do a thing. I wanted to do my thing. By that time, I had found my vocation, so to speak, because I had come across this forecasting methodology that involves logistic functions and S-curves. And as I left digital, I wrote my first book that's all about forecasting using S-curves and the natural growth processes. And so that was very exciting. And then I ended up doing my own consulting company, all the time, continuing publishing articles of my interest and teaching on the occasional circumstances. Even in Mexico, there was a leadership school they had in Monterrey that was giving MBLs, not MBAs, Masters in Business Leadership. And they invited me to give my forecasting course, on which I was an expert. So that at the end, I ended up, I'm still publishing articles, even though I'm semi-retired by now. And that's how this article came around. They invited me last year in Prague to talk about the singularity, the technological singularity. And while I was preparing the talk, I stumbled upon this relationship between entropy and complexity we'll talk about. And I got very excited, and then I ended up publishing this article that Bill saw and thought that we could present it at your show.
I'm curious if you consider yourself to be a systems theorist or a systems scientist.
I wouldn't give labels. I mean,
no.
By now I started as a physicist. I worked as a consultant. I taught. I was a teacher in several capacities. So I don't see myself as one particular thing. I even wrote a book recently on the story of the amazing life of my mother. So I became an author of literature, if you want. But things come as they happen to come in my life, and I do them. So I couldn't consider myself only as a physicist, or only as a systems analyst, or only as I worked on cycles for a while, but I wouldn't consider myself a cycle man either.
Yeah. All right. Well, I think that your work speaks for itself. So why don't we jump in and go ahead and start your presentation, and then we can continue the conversation and questions as we proceed and at the end as well.
Okay, this last topic on complexity that you mentioned came about first in 1999, when I visited my old friend and colleague Eric Schwartz in Boston, who had done our thesis together in Brookhaven decades earlier. And by now he was a a professor of cognitive and neural systems in the University of Boston. We hadn't seen each other for a long time. And then in the euphoria and the drinks and that evening in the talk, the topic came to the rapid change of rate of change, technology in everyday life. So
and about when was this? When was this, Theodore?
I put down
when was this?
That was in Boston.
I know, but when was it?
1999.
1999. Okay, got it.
And he says, let me show you the 20 most significant turning points in the evolution of the human system person, and that I put together. And let me show you. He showed me a graph. Now, what do you think the law behind it is? What governs this kind of growth process? I found it very exciting. I was already into growth process.
I mean, what were a couple of examples of events that he considered significant?
He says I covered the whole range. He says I started with the Big Bang, the first thing, and then I finished with internet and the human genome sequence.
So he tried to reduce all of the history down to 20 events.
The universal evolution.
Okay.
So we both agreed it's a fascinating topic. I said it would make a very good publication, but it very quickly became obvious to us that the crucial point is the data, because he had 25 points, no, 20 actually he had of his own, but there was a personal estimate. I mean, we couldn't possibly publish that as an objective study. So when I came back to Geneva, I took it upon me to find good, reliable data. He was busy teaching, research, other university duties he had. So I went after data everywhere, in the internet, in libraries, in publications, conferences. I even wrote to 60 Nobel laureates in physics, chemistry, and biology, medicine. And I asked them for their estimate of the 20 or 25 or so most significant turning points in the evolution of the universe. I got a handful of answers from those 60 Nobel laureates. And out of that handful, only one gave me a full set of 25 points. But I'll talk about it in a minute. So, but I did find many other. I ended up with 13 independent, reliable, and respectable data sets. And let me show you what kind of data they involved.
Great.
The example is a few examples of these 13 data sets where, you know, the list of Paul Boyer, the biochemist who gave me his 25 points, this Nobel laureate, major events in the universe of history, as was published in the Scientific American by two physicists, they had 23 points. Carl Sagan has a cosmic calendar. The 1st of January is the Big Bang, and the 31st of December is today. And in this calendar, he has put a significant event that took place. He has lots, about 47 such events. The Encyclopedia Britannica had its own list of 16 points. The American Museum of Natural History has another set of 20 points covering this range. And then conferences and symposia and so on. At the end, I finished with 302 data points. These 13 data sets had a total of 302 entries. And when I plotted them logarithmic paper, I saw that they were crowding together in clusters. Some clusters were very narrow, some were wider, but I went and calculated the average on each cluster, and I even calculated an error on this average depending on what the width of the distribution was. And then I ended up with 25 such evaluations, 28, which I called the canonical milestones. Because
so what we're looking at here is, you know, we're looking back in time to 15 billion years before the year 2000.
Present. The present is taking the year 2000.
And that's on
years before present.
It's on a logarithmic scale, right?
Logarithmic scale, yeah, 15.4 billion years until we get to the Big Bang and associated processes.
And then these are and so, there was a peak in significant events around 4 billion years ago. It was the highest peak, the highest cluster.
Yeah, they coagulate into clusters. And so I calculated the average on each cluster. So
and it's dissipating over time.
Right. Well, in a way, you're right. There's more measurements, but it depends who you are looking at. Some people the astrophysicists put more emphasis on astronomical phenomena, while the anthropologists put different emphasis. So depending on my 13 sets of data were collected, as I showed you, across the range.
Okay.
Now, when I published this in the Technological Forecasting and Social Change, a year later, they asked me to publish it on a more popular magazine, The Futurist. And The Futurist put this table. This is a page ahead on my article. And here you see that the first event is the Big Bang, and the last one is Internet and Human Genome Sequence. And in bold, I have the most important event in the cluster. And then the date is the average of the numbers. So somebody criticized because it says the asteroid collision here is 54.6 million years ago, but we all know the asteroid collision took place earlier, later, 64 million years. So the difference is that I'm putting the date of the average of all the events in the cluster, and I'm only highlighting the most important to give a name to the milestone. So 2 years later, this is 2000, maybe 3 years later, 2005, Kurzweil's book came out, The Singularity is Near.
Right, so that was Ray Kurzweil. And
yes, in that
phenomenon, book, very popular book, The Singularity
became a bestseller
is Near.
very quickly. But he used this data, exactly this data. He presented it in different ways. But 4 central graphs in this book, plus other with runaway trends, led him to conclude that we are approaching in technological singularity.
So did he use your data set literally?
Exactly. This exact data set, not even the one from Technological Forecasting and Social Change, who was more scientific, let's say. He took this data and he plotted them in a different way. Like he plotted them as the time to the next milestone. So the difference to the next milestone. And he got this graph, which is a log graph, and it seems a straight line. In fact, if I put a straight line, this red line, it does good justice describing the data, except for a little bit in the recent times. But there were other deviations before. So one can be tempted to ignore this as a fluctuation. It would be the wrong assumption to make, because if we extrapolate now this line and we go to 1 year before year 2000, we should be having milestones every 7 or 8 months. And if you extrapolate further, you go to 3.5 days before year 2000, you should be having a milestone every day. So obviously, this cannot continue. I wanted to analyze this data in a different way. I hadn't seen this anyway. I wanted to calculate the complexity introduced by each one of these milestones, and possibly to calculate a number for this complexity.
So I just want to go back to that chart for just a second, though, because to me, that chart, I mean, this is a very simple thing that you've done that I don't, not necessarily everybody in our audience will appreciate or understand right out of the gate, but this chart ends in 2000, right? And even what you've done here of just extending the chart, from about 10 years before 2000 out to 3 days before 2000, right?
Yeah, because the straight line, one is tempted to do this kind of extrapolation.
Predicts that you will now be seeing, events on the scale of like, the first multicellular life happening
on the scale of nuclear energy, on the scale
of nuclear
transistor.
energy, right? Happening every 3.5 days.
Every day, a new event like this.
By 2000, right? Let alone
by 3 days before 2000, by 2000, it will go to infinity.
Okay, right. So, I mean, to me, this simple explanation kind of makes the whole singularity ridiculous.
Yes, that's right. Okay. Why didn't Kurzweil feed a straight line and say, okay, let's extrapolate? But anyway, now what I wanted to do is I wanted to calculate the complexity introduced by every milestone. Mm-hmm. And I said, the importance of every milestone is proportional to the amount of change, the amount of complexity it introduces, plus also proportional to the time, to the duration of the ensuing stasis until the next such event takes place.
Okay, so that's delta change times delta time.
Yeah, if the change is big, or if it lasts for a very long time, then it's very important. That was a simple argument, the way physicists think.
Yeah.
And then this way, the complexity introduced is inversely proportional to the time to the next milestone. And
so can you just give us an example of that, looking back at an event? Well, like what's an event that had large complexity?
As the time is getting crowded together, remember from Carl Sagan's calendar to the rest of the graphs I showed you here, the milestones get crowding together towards recent times. So as they crowd together, the complexity gets bigger and bigger. If the importance is to remain the same, the area, the shaded area in the squares is all the same. And
so the shaded area of each square is the importance.
That's the importance. If we assume it's the same, there's maximum importance. So I made the approximation, it's equal importance. I agree, this is pushing it a little bit, but between maximum and equal is not a big difference. So if you assume they're equal, then as they get crowded together, the complexity introduced is bigger and bigger.
Yes, got it.
And so I was able to calculate a number. This is an arbitrary unit, of course, because we don't know what the importance is in absolute sense. But if you're taking the ratio between adjacent milestones, you get a relative, in relative units, you get a complexity estimate and even an error depending on how wide the cluster was of events on that particular milestone. And here we come back again to the discussion with my friend in Boston. What kind of law describes this evolution? Because a straight line is obviously not a good law. So at this point, Richard, I want to take a break and talk about the natural growth process. That is
but let me just, like, one of my jobs, Theodore, is to make sure that the audience understands what they're looking at, right? Because we're not talking to a bunch of fellow physicists necessarily. But so what we're seeing here is that as these are the 28, canonical milestones. And as they get closer together, as they cluster in time closer to us, their complexity rises because you're saying that they're all equally important.
Right. Okay. And if they get closer, that means they're more and more complex. Yes. Because I assume the importance is proportional to both the stasis and the amount of complexity introduced.
Yes, got it. Very good.
So now, before we try to put to fit any lines on this, I want to change the subject a little bit and go to the natural growth process.
Which is the sort of process that you really built your career around.
Exactly.
These natural growth processes are like populations.
Right.
Which is what Edward Dewey actually, one of the things he started with back when he created the foundation for the study of cycles.
This process is ubiquitous. That's what I'm trying to point out here. It's the size of an organism that grows like a population. That is, if you put two rabbits on a fenced-off grass field, the two will become 4, the 4, 8, 16, 32. There will be exponential growth in the beginning of the population, often referred to as population explosion. But to the extent that they arrive at the limit of the grass available and the capacity of the field to feed the number of rabbits, the population will slow down. The growth of the population will slow down. And the overall trajectory will be S-shaped. That's why we call it an S-curve. And it will saturate at a ceiling, which represents the amount of rabbits that can survive on this fenced-off grass field. In fact, there may be some oscillations because if they multiply anymore, they will starve. There will not be enough grass. And then as they die, the grass will get a chance to grow again. So they will be able to multiply again. So there might be oscillations on this homeostatic level, at equilibrium, homeostatic equilibrium at the ceiling, which represents the capacity of the field to feed a certain number of rabbits. Now, when I was working for the computer company and I presented exactly this graph, I mean, this graph was from that times, to marketeers, they objected by saying, we build computers. Why are you talking to us about rabbits? What do computers and rabbits have in common? And then I had to bring out this joke I knew, which is they can multiply. Now, but it's not only computers and rabbits that grow the same way. As I said, this curve is so ubiquitous that you can find all kinds of things in society that follow this trajectory. In fact, one of my most frivolous examples in the book is Mozart, who individual productivity and creativity follows this curve. So that if you follow the Mozart's compositions, if you put them down as a function of time, you see that they follow an S-curve, which is almost complete when he dies. And the respective chapter is called Mozart Dies of Old Age, because when he died, he had practically exhausted his creative potential because his curve had flattened towards a ceiling. But since we are at the foundation of for the study of cycles, I want to bring another application of S-curves concerning world energy consumption worldwide. And here is the last 200 years of world energy consumption per capita worldwide. I even updated this last week. This red dot is year 2020, and it's down because of COVID. But you see how the data wiggle around the natural growth, the S-curve, the logistic function, the thick gray line here. And if you isolate it, simply take the ratio of the data to the line, you extract a cyclical pattern, which is no other than the Kondratieff cycle. The Kondratieff cycle was originally determined from econometric variables. Here we have it falling out from a physical variable like energy consumption measured in joules. And we see the thick gray line here is a cycle of a period 56 years. And the data agree fairly well, even though they fall somewhat apart aside the 2020 point, which is because of COVID. Even before that, that decade shows some deviation. But there is obviously a cyclical pattern here. And there is a theory that the Kondratieff cycle could be due to periodic climate variations. If that is the case, then I have another graph here, which I updated last week, the number of major hurricanes per decade. And here again, we have the gray cycle is the same 56-year cycle that you saw on the previous graph. We see again the data agree very well, And the last
so
point,
these are the deviations from the trend, right? So a
yeah,
linear trend.
There are some deviations, but I mean, I consider this to be in good agreement, particularly the last point.
But the data that you're plotting
no, you're right.
are the deviations from the trend.
There's a very gentle linear trend. It's not very much of a trend, a straight line trend. And so these are the deviations from the straight line trend.
These are the deviations.
But even if
from
you
the straight line
don't
trend.
take the trend out, you see the same pattern as the gentle trend goes up.
Got it.
So there's no manipulation here really in terms of data presentation. So see here we have a complete 3 periods over the last 180 years that seem to be no deviation, in fact, good agreement with the last data point that updated last week. Oh, the cycles is a big topic, as you know very well. So I don't want to go farther into this topic. I want to go back to the discussion of our complexity issue. And I want to give some popular definitions for complexity. The most obvious definition is how difficult it is to describe something, a system. If the system is complex, it's difficult to describe. If it's simple, it's easy to describe. So complexity is low for an easy system to describe and high for a difficult system to describe. And entropy, the most popular definition of entropy, is a measure of disorder, which can only increase according to the second law of thermodynamics. In a closed system, the disorder can only increase. So let's take a couple of examples now. Mixing coffee with cream. If you put cream on top of your coffee and you don't stir it, the coffee sits on the bottom, the cream sits on the top. This is a system easy to describe, so relatively low complexity. And then there's order here, you know, they're well separated, so low entropy because the disorder is low. If you start mixing, you reach a state where things are very messy and it's very difficult to describe in detail what's happening. So complexity is high. The disorder is high too. So entropy is high here. But if you continue mixing to the very end so that it's completely uniformly, cream and coffee are completely uniformly mixed, then it becomes again easy to describe. It's trivial, in fact, because it's just one color, but the disorder is maximum because if you consider that every cream particle and every coffee particle has its own velocity and position, and not two of them are the same, and they're all over the place, that's maximum disorder, maximum entropy. In fact, entropy stops increasing. Here is equilibrium. That's the end. So we see that in this process, we went from low complexity to low complexity, going by high complexity in the middle, while entropy kept increasing continuously, monotonically, according to the second law of thermodynamics. Now, so complexity follows a bell-shaped trajectory, goes up and down at a time where entropy follows more or less an S-shaped trajectory, because in the beginning it grows sharply as we start mixing, and at the end, as it arrives at maximum value, it is an asymptotic. It approaches asymptotically, relatively slowly, until it stops growing altogether. So we're having a bell-shaped trajectory matched to an S-shaped trajectory. So already there is, from that discussion already, we see that they may be related in a way of derivative to integral, the two of them. And that becomes obvious if we take the more serious definitions for entropy, the Shannon information theory, information-related definitions. So we have something like entropy is the information content, and complexity is the capacity to incorporate information at a given time. From these two definitions follows directly that entropy is the accumulation of complexity. as you go over the cycle of complexity and you add more capacity to incorporate information, the entropy grows. So we end up with this kind of picture, both for the cup of coffee and cream, and for the whole universe for that matter, because the whole universe in the beginning, the early universe, was rather orderly and low entropy and low complexity. It was just a uniform plasma expanding at the Big Bang time I'm talking about. And then at the very end, again, when everything is everywhere, where particles and energy are spread around throughout the universe, the so-called heat death, where there is no differentiation, entropy has reached its maximum value. Complexity will be easy again because it will be system easy to describe. So obviously, what you see here, what I showed you, the blue curve is the logistic function, and the red curve is its derivative. But they match qualitatively, at least, to the concept of entropy and complexity. So I would like to propose a new definition of complexity. In fact, there are many definitions of complexity. Somebody has tabulated 31 definitions for complexity and many for entropy. But what I'm suggesting is that we call complexity the time derivative of entropy, and consequently, the integral of that, the integral complexity, gives entropy. This is what I put in my latest publication. This is rigorously true for the definitions I just mentioned. But if you assume that all definitions for complexity and all definitions for entropy are somehow related to each other, then this relationship should somehow hold in more general terms. But this is debatable, so I'm not going to push in that direction. Let's go back now.
So does that hold true in the Shannon information theory?
This is rigorously true according to these definitions. Entropy is defined as information content in Shannon theory. Complexity is, I define it, the capacity to incorporate information. It's a definition that has been given often. So
let me
just definitions.
When I think about Shannon entropy, Shannon information theory, in my mind, I always think about
probabilities.
A die, right? A dice, like dice,
yeah.
Right? So if you have a fair six-sided die.
Yeah, you
right?
have in mind the definition which says the logarithm of the probability, and it's
sum of p log p, right?
Yeah, that is a mathematical. You're right. Shannon is more in that way, but that is well. You have to think of a closed system. I don't know how the die represents a closed system. I'm saying that, well, you maybe we take Shannon out. If we assume these two definitions, then it's rigorously correct. For other definitions, it remains to be seen.
Okay, got it.
The information content, the information content in the early universe was low, and in the ultimate, in the heat death, information content will be extremely large, because every single particle in the universe will have its own velocity and position, and to describe that, you will need immense amounts of information. So what I want to get to is my old calculation here of complexities, and try to see if I can use these ideas to determine an evolution for this process. So if we accumulate now these values, take the integral of these values, we end up with this data set to which I fit an S-curve that is this thick gray line. On the bottom, I showed you the same data with vertical logarithmic scale to show you how well it fits the data all the way back to the Big Bang. For the most period, the evolution is exponential. It's a straight line. but it begins deviating in recent times. And the thin black line is a simple exponential that continues a straight line on logarithmic paper. The thick gray line is the S-curve. What's interesting on this view is that the 28th point, when we have draw the red line, we don't have a complexity estimate for this point because we don't know how far is the next point. But on the 28th data point, we are 50%, 50.1% penetration of the S-curve. We're in the middle of the process. And this becomes much clearer if we take the rates of change. And we see that this is the graph I showed you earlier. And this is in linear scale. It's the bell-shaped derivative of the S-curve. And you see here that the deviation from the exponential is flagrant in recent times. Now, from this, now we have a forecast, if you want, either by exponential trend or by S-curve trend. And with this forecast, we can read off a complexity value and therefore determine a time when it will appear. So I can deduce a forecast by logistic fit or by exponential fit for the next milestones. And that's what I've done on this table here. Here we don't see, maybe we take off the pictures because we don't see the values of the exponential fit. The logistic fit says that the next milestone should be in year 2033, while the exponential fit, can we take off this? Oh yeah, here like this. Does this make sense? Okay, so here I lost your sound.
Oh, sorry, I can see the full chart. And
yeah, okay,
I see
good.
the 2009.
So the exponential fit says 2009 for the next milestone, and the S-curve says 2033. The next one S-curve is even farther. The 30th is 278, while the exponential is 215. And in short, the exponential fit says that by 2021, we should have seen 5 of these milestones, while this doesn't agree at all with the logistic fit. And so the conclusion is that we are experiencing the world in its most complex state. That's the maximum rate of change. And we could expect to begin the beginning of a slowdown in the amount of complexity and change in our lives. And never mind for the technological singularity, that doesn't make sense. But people have a hard time swallowing that the complexity will go down in our lives in the near future. And
what does that mean to you? What would that look like?
Well, life will become simpler rather than more complex. Well, I have here some examples. Science has a tradition of condensing knowledge. Like Maxwell's equation simplified the magnetism-electricity mess. There was very complicated descriptions before Maxwell put it all in 2 simple equations. The same way with the particle physics. They're searching for the grand unification theory because they have 300 particles or so that they have a hard time classifying or integrating. And I'm pretty sure that they will get to it sooner or later. I remember the transistor when I studied engineering. We studied the transistor. It was a question for weeks and chapters in books to study a single transistor. And today you have young men, almost teenagers, who could manipulate millions of transistors in a chip without ever having to go into this detail of how you bias the collector and the emitter in a transistor. And of course, we saw in the coffee and cream and the universe examples that complexity goes up and down. Complexity goes down when things get extreme, extreme disorder, very large values of entropy. when entropy starts approaching asymptotically its maximum value, it goes very slowly towards that maximum, then complexity becomes very small. So my feeling is that the next couple of milestones could well be around 2033 and 2078. The question is, what could they consist of? And here I mentioned earlier that Paul Boyer suggested two future milestones. The first one, human activities devastate species and the environment. And the second one, humans disappear, geological forces and evolution continue. These are rather pessimistic, hard to swallow, but still, I think there will be more scientists to agree with my dates and these suggestions rather than with imminent technological singularity. But we don't have to be so pessimistic. A less pessimistic approach could be that the next couple of milestones could be, the first one could be a cluster of achievements in artificial intelligence, robotics, nanotechnology, bioengineering, man or woman in Mars. I know NASA has plans to put someone on Mars by mid-30s. We saw this phenomenon at the turn of the 20th century. There was a cluster of achievements there, electricity, telephone, aeroplane, automobile, modern physics, all of these events clustered around the turn of the 20th century, and they count for one milestone, one canonical milestone. So a similar milestone could be around 2033. And then the next one for 2078 could be something like a teleportation or creation of life, which sounds very science fiction-like today. But I know there's work, there's research going on in both of these directions for some time now. So can I talk about one more? Let me stop this. There is one more curious example that I want to mention, a curious phenomenon that is tangential to all this, and that's the baby boom. Now, the baby boom is a phenomenon not well understood today. There's a simple explanation that soldiers came back from the war and they indulged in making babies. Well, that's not correct. And I'll show you why it's not correct. So you see the number of births per thousand population in the 20th century was declining, and it did so in a natural way, which is this can be described by an upside down natural S-curve, natural growth, natural decline curve, all the way to the 30s. And then we have this bump to finish and then catch up with the same trend much later. We can isolate this bump, subtracting the data from the trend I fit. And here we see a very clean natural process again, which is the baby boom. It starts in the mid-30s and it ends in the early 70s. So no connection to the war. The war is this one here. You see this fluctuation went down for a few years and up afterwards when the soldiers came back. But the whole baby boom is not related to the war. So now if you take 80 years of age as the average lifetime, this number of births translate to this number of deaths. And if we take the span of this time and we put it on top of our curve before, we see these are the indicated by the orange lines.
That's 80 years between the orange lines.
Straddles the peak. And it exactly the last 3 data points. In fact, this is the only time in the whole evolution of the universe that 80 years could accommodate 3 canonical milestones. So that's why I have described this in some occasion as we're sitting on top of the world, because the baby boomers, for some reason, were lucky enough to benefit from the period of the highest rate of change, the highest complexity in our lives.
Mm-hmm. Wow.
So, as I said, this was kind of a cute observation.
Very interesting. So if I attempt to sum up what you've just shared with us, right, it's that I would say that these S-curves or logistic curves, growth curves, right?
Exactly.
Are kind of the definitive structure in evolution, and also apply to the evolution of the universe.
Right.
Right. And Mr. Kurzweil was making some assumptions to, for his sensational bestseller, The Singularity is Near, that really involved exponential growth, continuous exponential growth, right? Instead of a leveling off, as happens in all growth processes, right?
Right, because nothing is infinite in natural processes. I mean,
right. I never liked Kurzweil's book. that's why I was
never read
interested
the
in
whole
your.
thing. I've been very critical. I've been made. I was asked to review it, and I was very critical. And
it hasn't come true, right? I mean, there haven't been.
No, it hasn't. I mean, we haven't seen
an
it.
accelerating series. Although, I did. Some people might look at something like Bitcoin, for example, and consider that
is important.
a
Would
big
you say
change.
Bitcoin is as important as the internet?
There are people who would argue that it is as important as the internet.
Oh, really?
I'm not
but...
quite there myself, but there are people who do argue that Bitcoin is truly a revolutionary event.
I would be willing to put it down as one of the cluster that will be centered around 33. That's probably a big cluster, a wide one. And one of them could be the Bitcoin, if it proves itself until then.
Right. And how about, what's the biotechnology that's going on today?
Oh, there's a lot. There's a lot.
Right? I mean, there is a lot. I mean,
but not a single one that would say that, the
CRISPR technology. How about the CRISPR?
Yeah.
Right?
Sure.
So, I mean, there is a lot of change going on today.
Right. I mean, that's the most provocative statement I make, and I want to stick to it, that this change is not going to keep growing, that it will begin tapering off. In an obvious but not real way. It happens because cars become easier to drive, telephones become easier to use, but that's not real because beneath the hood they get more complex. So that's not an argument that's not proof of what I'm saying. But I think sooner or later it's the old feeling that when some variable gets too big, things get reversed. Like even though Kaufman says that how overly connected network is as non-functional as a poorly connected network. It's the normal distribution. The bell-shaped life cycle is very close to the normal distribution, very close. So so many things are normal in life, and I know John Casty, I don't know whether you know him, he told me that, entropy is just complexity, the same thing. And he says, look, if somebody has to decide whom to hire and has only one candidate, his life is simple. If he has 10 candidates, his life is more complex. The more people he has to choose from, the more complex it is. And then I argue, but if he has 1 million candidates, his life will be simpler because he's going to adopt different ways of choosing. Maybe first come, first serve, or whatever. But he's not going to go through 1 million people. So it's not going to be as complicated as having 30 people to decide from. So I can see this coming from different angles, and I expect it to be true.
Yes, makes sense. Well, I could say I'm ready for a little less complexity in my life.
Everybody is.
And I guess last question, it does seem remarkable, maybe even, what would we say, anthropic,
Yes.
to say that, to have the data turn out that we're living at the pinnacle of the universe. Have you questioned that yourself?
Yes, in fact, when I tried to publish this article, some of the reviewers objected to that.
Mm-hmm.
And they made me go back and refit the data with a shorter range.
Mm-hmm.
And but if you take, I have here, let me share one more screen. So if you take only the more recent 16 milestones,
mm-hmm.
these are related to humans. They start with the first stone tools, first humans, Ice Age, Homo erectus, etc. And then domestication of fire, differentiation of DNA. And you take only this data,
mm-hmm.
the result is identical. Because for the most range,
interesting.
The far past, the range was purely exponential. It started differentiating itself in recent times.
Mm-hmm.
So even if I take half of these,
mm-hmm.
the fit doesn't become significantly different. Mm-hmm. So is the last few milestones that determine that we have to go for natural curve, for an S-curve rather
mm-hmm.
than exponential. If
mm-hmm.
you stay on the older times, and it's a coincidence, it's an interesting coincidence that even the early data fall on the same line, but it's a long exponential all the way to recent times. Mm-hmm. So by restricting to more relevant, so to speak, events, mm-hmm. the result, the analysis doesn't change. We get the same result.
That's very interesting.
Yeah, it's fascinating how we fit today, we extrapolate backwards, and we pick up even the Big Bang on the same curve.
Very interesting. And I wonder also, this connection that you've made between complexity and entropy mm-hmm. is very interesting to me. It certainly looks good on paper, right? When you take the derivative of the S-curve and get the bell curve. I wonder, have you gotten any feedback on that from the wider community?
No, feedback on LinkedIn and then, mm-hmm. in the media and mm-hmm. from friends and so on. Mm-hmm. But there are criticisms like the subjectivity of the milestones and mm-hmm. no, but this is not irrelevant.
Are you planning on developing this idea some more about the relationship?
I don't know. I did target several hundred colleagues and friends, mm-hmm. science-friendly friends, mm-hmm. With this idea, and I expect. I only did this recently. I expect that they will come back and say their objections. Mm-hmm. Old colleagues from CERN. Some physicist told me, you are pushing it a little bit, he says. And then what happens, he says, if you, in equilibrium, you have no growth, constant entropy, that means the derivative is zero. So we have zero complexity. So I said, look, in equilibrium, the complexity is indeed very low, because it's very easy to describe. Now, if it's zero or if it's arbitrarily small, I mean, these are academic questions. You don't want to really to push it to these extremes. And my point is that this should be a guidelines, useful guidelines. Mm-hmm. So even when Casti told me entropy is complexity and vice versa, there's no difference between the two, mm-hmm. which to me is obviously wrong. Even then, my relationship gives some guidelines in the region where entropy grows exponentially. Entropy grows exponentially, its derivative grows exponentially. So he's right, entropy mm-hmm. and complexity are very similar. And my relationship gives guidelines in that direction. But mm-hmm. that's an extreme, and the definitions are so, to my mind, wrong. So it remains to be seen. I hope, as I said, I told you, if you find people to give me feedback, I will be eager to discuss with them.
Very good. All right. Well, we really appreciate your time and you sharing this work with us.
Thank you.
Very
It was my
interesting.
pleasure to talk to you.
Thank you so much.
Thank you. Bye.
Bye.